So our next topic is ABCD parameters, which is also called as transmission parameters, and we have some alternative names also, which are general circuit parameters, which is also called as general circuit parameters. Otherwise, we can call it as chain parameters. Why? Because these are used in cascaded type networks, so that's why we can call it as chain parameters. Okay. ABCD, transmission, general circuit, and chain parameters. You can use any of these names, okay? And this is our standard two-port network model. So this is port 1. So this one we can call it as sending point also, right? And the variables here the variables are V1 comma I1, and this is port 2. So in this ABCD parameters, we can name it as a receiving point also, and the variables are V2 comma I2. Okay, so in this transmission parameters, you can transmit the energy from a source to destination. Okay, in general, so the energy can be transmitted from one point to another point. The sending point we can call it as source, and the receiving point we can call it as destination, right? Otherwise load. Okay, this we can call it as source. Okay, and this one we can call it as a load, otherwise a destination. Okay, destination. So the energy can be transmitted from source to load. Okay, so at a time we can that means we can start from one point to another point. For example, so this is your source, and we have in between we have some network is there. This is one some network. We have different types of components here, and at the end we have one load here. Okay, this is source, and this one is our load. Okay, now we can transmit the energy from source to load with the help of this particular network, with the help of this particular network. Okay, so in this concept, so we are transmitting from source to destination, right? So that means we can drive this entire energy from this source point of view, right? From this source point of view, when we are talking about the standard two-port network model, so we are driving the energy from port to 1 onwards, right? We are driving the energy from port to 1, uh, and we can collect the energy at port 2. So that means this is one way of transaction. So this is one way of transmission, right? So that means for example, if you assume this one as a port 1, this entire thing we can call it as a port 1. Just you can assume this one as port 1 and this one as port 2. Now you are connecting 5 volts AC or DC, whatever. Okay, AC or DC source here, and from this we can contribute the 5 volts of energy through 5 volts of energy to this particular network. That means this network act as a medium, right? This network act as a medium, otherwise path, okay, to transmit, to carry this particular energy uh, to the load, right? So wait a second. Okay, so that means for example here I am taking current due to this 5 volts of voltage, so we are getting certain amount of current. Just I can name it as I1, right? So this I1 is distributed to these all elements of this particular network. So after that whatever the amount entering into this particular network, same amount of current can be leaving through this particular network, so that here also we can expect I1 amount of current, and this can be transmitted to this particular load, right? This is in the one way of transmission, so that's why I'm taking current direction in this way, and same current can be transferred to here, and again we can get it I1 here in the case of DC source. In the case of DC source, right? So and same current can be circulated this entire loop. Okay, so if I am taking one-way transmission from a driving point to ending point, driving point is nothing but source, and this is your driving point here. Okay, and this one is the ending point, otherwise we can call it as load, right? So the energy transmission can be taken place from driving point to load. So that's why here we are taking I1 current direction in this fashion, and here also the current direction can be taken in this fashion, I1. But in our standard reference two-port network model, the current direction at port 2 indicated in this direction, but according to our transmission parameters, the current direction should be in uh, towards the second terminal, right? That means the current direction is like this. Okay, in our assumption. Okay, that means according to our theory, so this is the driving point, this is the load. So we are transmitting the energy, we are driving the energy from source to destination, so that we can get one way of transmission. Okay, so according to that assumption, here we are getting current direction in this way. That means యాక్చువల్లీ I2 అనేది మనకి ఈ డైరెక్షన్లో ఉండాలి, బట్ స్టాండర్డ్ రిఫరెన్స్ మోడల్లో I2 అనేది ఈ డైరెక్షన్లో మెన్షన్ చేశారు. కాబట్టి ఇప్పుడు మనకి యాక్చువల్గా I2 ఏమవుతుంది, -I2గా కన్సిడర్ చేయాల్సి ఉంటుంది compared to reference model. According to our assumption, current direction is in this way, but according to this standard reference model, I2 is indicated in opposite manner, so that whenever you form the equations, you can take it as -I2. Okay, based on our assumption. Okay, and for this we are taking at a time one source. That means you are considering port 1, otherwise port 2. Okay, that means uh, the energy contribution can take place either port 1 or port 2, that depends on your choice, right? But we can start the energy contribution at one point, right? Whether it is port 1 or port 2. ఫర్ ఎగ్జాంపుల్ ఈ ఎగ్జాంపుల్ తీసుకుంటే మీకు ఇక్కడ 5 వోల్ట్స్ దగ్గర నుంచి ఎనర్జీ కంట్రిబ్యూషన్ అంటే ఎనర్జీ డిస్ట్రిబ్యూషన్ అనేది స్టార్ట్ అవుతుంది త్రూ దిస్ ఎంటైర్ పాత్ని యూజ్ చేసుకొని, ఎంటైర్ నెట్వర్క్ని యూజ్ చేసుకొని లోడ్కి ట్రాన్స్మిట్ చేస్తాను. అంటే వన్ పాయింట్లో స్టార్ట్ అయిపోయి నెక్స్ట్ పాయింట్లో ఎండ్ అవుతుంది. ఓకే, అది మీరు పోర్ట్ 1 దగ్గర అయినా స్టార్ట్ చేయొచ్చు అండ్ పోర్ట్ 2 దగ్గర అయినా స్టార్ట్ చేయొచ్చు. ఓకే, సో ఇన్ కేస్ పోర్ట్ 1 దగ్గర స్టార్ట్ చేస్తే అక్కడ V1 I1 వచ్చేసి డిపెండెంట్ వేరియబుల్గా యాక్ట్ చేస్తాయి. ఓకే, సో ఇఫ్ యూ స్టార్ట్ ద ఎనర్జీ డిస్ట్రిబ్యూషన్ ఫ్రమ్ పోర్ట్ టు 1, so that we can consider V1 comma I1. These two are dependent variables, and V2 comma I2, we are collecting the energy at port 2. That means the port 2 act as a load, so that's why we are taking V2 I2 are independent variables. So from this dependent variables means these variable located in left hand side, and these independent, that means these variables are function of these independent variables. Now we are getting V1 I1. So here V1 equals to A V2 minus B I2. I already told you, whenever you are considering I2 current, so you can take negative, that means minus sign. Okay, why? Because according to our assumption the current direction is like this, but based on our standard model I2 is in reverse mode, so that's why I'm taking minus I2. So AV2 minus BI2. Okay, otherwise you can mention in this way, plus B minus I2. That is better, right? And in the case of I1, CV2 plus D minus I2. So now what you will get? So this V1 I1 equals to AV2 minus BI2 and CV2 minus DI2. This is equation number 1 and this one is equation number 2, right? Now you can form a matrix form, that is V1 I1, then you will get ABCD matrix, and then you can take independent variables, that is V2 minus I2. So this is your matrix format of transmission parameters, and this is your ABCD matrix, the rest transmission matrix. Okay, and now you can evaluate the ABCD parameters. That means you can evaluate A value, B value, C value, D value, right? So for that you can take these two expressions. Okay, so now we have two cases. First case one, in order to find out this A value, you can make it as you can make it I2 as 0, right? So if I am taking I2 equals 0, that means what? Port 2 act as an open circuit at port 2. So that is the meaning. So while making I2 equals 0, we can able to find out two things. One is A value and C value, right? So from first equation, we can evaluate A, and from second equation, by making I2 equals 0, we can evaluate C value, right? And in the same way, we can take second case, that is V2 equals to 0. So V2 0 means what? Port 2 act as short circuit. Port 2 act as short circuit. Okay. By making V2 equals 0, we can able to find out B value and D value, right? So now you can take A equals to and C equals to, and here B equals to and D equals to. Now A equals to what? While making I2 equals 0, we are getting V1 by V2, okay, only when I2 equals to 0, okay. And when you are taking, so now if you observe this, so V1 by V2 means what? Obviously that is a gain, right? So we have numerator also voltage and denominator also voltage, so that is nothing but voltage gain. But from where to where, that is important. Okay, output is port 1 and input is port 2. That means 2 to 1 movement. Okay, input, always we are traveling from input to output, right? So the input terminal is port 2 and output terminal is port 1. That means 2 to 1 transmission. That will be considered as a reverse mode, right? So reverse transmission, right? So now you can name it as a reverse voltage ratio, a reverse voltage gain or ratio, so whatever. Okay, reverse voltage gain. And when coming to C, so I1 by V2 only when I2 equals to 0. I by V is nothing but what? I by V is nothing but admittance, right? I by V is nothing but what? Admittance. But here the output is located at port 1. Okay, output is port 1. This is output, and second port considered as input. Okay, always we are transferring from port input port to output port, so that's why which is called as transfer admittance. Okay, that's why we call as a transfer admittance. The transmission can be taken place from port 2 to port 1, so that we can call it as a reverse transfer impedance admittance also, right? A reverse transfer admittance also, no problem. Okay, this is transfer admittance, this is voltage gain, reverse voltage gain. And when coming to this one, B equals to what here? uh, V1 by I2, right? V1 by I minus I2, right? If you make V2 equals to 0, from first equation we are getting B equals to V1 by minus I2 only when V2 equals to 0. Now what is the name for this B? So this is V by I format. So V by I is nothing but what? Impedance, right? So and which is starts from port 2, and this can be end at port 1. That's why we can call it as a reverse, right? So reverse impedance, right? But we can call it as transfer impedance. Transfer impedance. Okay. So this is transfer admittance, and this one is transfer impedance. And next, when we consider this D, so we are getting I1 by minus I2, right? I1 by minus I2 only when V2 equals to 0. So which is called as uh, current ratio, right? So here also we are starting from port 2 and we can end at port 1. This is also called as a reverse, right? So for all these parameters, we are getting a reverse voltage gain, a reverse transfer admittance, and a reverse transfer impedance. And here we are getting a reverse current gain, reverse current ratio or gain. Okay. So for all the parameters, reverse is the common thing, so that you don't need to mention this reverse. Okay, just you can consider voltage gain. A is nothing but voltage gain, and C is nothing but transfer admittance, and B is nothing but transfer impedance, and D is nothing but current gain, otherwise current ratio, right? So this is about ABCD parameters, and the next one, symmetry and reciprocity condition. First, we will take symmetry condition. Symmetry condition. So here, if A equals to D, if A equals to, wait a second, if A equals to D, so which follows the symmetry condition. And the next one is a reciprocity condition. A reciprocity condition. And to follow this reciprocity condition, we need to satisfy this equation AD minus BC equals to 1, then it follows the reciprocity condition, otherwise it won't. Okay, next we will look into some applications of this particular transmission parameter applications. So the first application here is so these parameters are used in transmission line theory. Transmission line theory. And the second one, and which are used in cascaded networks. Okay, and the third one, which provides direct relationship between input and output. Okay, these are the three applications, and especially this is transmission line theory if you are taking power generation to power utilization point. Okay, generally power generation can be that means that power generation can be possible in various formats. Okay, coal based generation, and water based generation, and wind based. So like that we have various methods to generate the power. So from that point, from that generation point, so we can transmit the power through transmission lines. So in the beginning of this network theory class, I already explained. So these are the certain transmission poles. Okay, these are the transmission poles. Okay, and these are the conducting wires, right? So these are the conducting wires. So like that we have various points. So from this point to this point, okay, from this point to this point, this entire path will act as one particular circuit, right? And again, if you take one more pole, so here also we have a conducting conducting wires from this point to this point. Okay, this will also make one particular circuit. This is one particular circuit, and this is also one particular circuit. These two are what cascaded, right? These two are cascaded. Okay, so that's why I'm using used in cascaded networks also. If you are taking the transmission line path, entire path, okay, so that will constructed with the help of cascaded networks only. Okay, and for this transmission line theory and for this transmission, what is the relationship? Okay, so we are not directly applying transmission parameters to this particular configuration. Okay, so first we can take it as a equivalent model of this transmission lines. Okay, here we have certain power generation station, and here we are using some industrial application or a household application. This is source, and this one is the destination, right? The source is we have various generation stations, right? So generation station is the source, and the destination is what your household applications, otherwise industrial applications. The utilization of that power is nothing but destination, right? So now from the source to destination we need to transmit this entire power. So for that we are establishing these transmission poles and these transmission wires. Okay, transmission wire is nothing but conducting wire, but these four lines is separated by certain distance, right? And each and every conductor is act as a resistor, and I mean each and every conducting material will have certain amount of resistance, so that entire path having certain amount of resistance, right? Entire path having certain amount of resistance, and there should be a induced EMF along with these conductors because of their construction. Okay, because of their construction, so that's why we are getting parasitic inductance also. Okay, and the four conducting wires are separated by certain amount of, for example, if you take two conducting wires, these two are separated by certain distance means, so this will be form a capacitor or not. Two plates are separated by certain amount of distance means which forms a capacitor. In this conducting wires also, which are separated by certain amount of distance, so that's why we are getting capacitance also. These all three are not present directly here, right? But which are involved in indirect manner. So these are hidden things, right? While making this configuration, while making this construction, so these values are not directly present, but indirectly these elements are involved in this particular construction. These hidden RLCs are called as a parasitic effects. Okay, parasitic resistance and parasitic inductance and parasitic capacitance. Okay, so due to that means this entire path from this pole to this pole, so we have four conducting wires. These conducting wires will forms one RLC network, one RLC network, whether it is series or otherwise whether it is parallel or series and parallel, whatever. Okay, there should be a RLC network from this pole to and this pole, and again we have like that, so many poles are there, and one pole to another pole we have to cascade these conducting wires. That means we have so many RLC circuit, all are cascaded, right, to transmit this particular source, transmit this energy from source to destination. So in order to evaluate such type of cascaded networks, we are using these transmission parameters, and especially which are very helpful in transmission line theory, and which provides the direct relationship between input and output. Means this is your input, the source is your input, and this destination is your output, and we can maintain the relationship, direct relationship between input and output with the help of these transmission parameters. Okay, and one more important thing, and so while transmitting this energy from source to destination, this is a one-way transmission, right? From source to destination, we are transmitting. Okay, so that's why I'm taking current direction in this particular standard two-port network model in a single direction. So in that, based on that assumption, I'm taking here minus I2 while comparing to the standard model having reverse direction, but our assumption is the forward direction, so that's why I'm taking minus I2 here. Okay, so this is about ABCD transmission parameters. So we need to prove this cascaded networks. Okay, how it will be applicable, that we will take one example. Okay, we will take one example and we can apply this particular transmission parameters. Okay, okay, I will make okay, I will give one question. Okay, two-port networks, two-port networks are connected in cascade manner. Prove that overall transmission parameters are multiplication of individual individual transmission parameter matrices. This is your question. Okay, so now first of all, the question basically focuses on cascaded type of network, and that too they are mentioned two-port networks are connected in cascade. First we will take first two-port network. So this is your first two-port network. Okay, I can name it as uh, and this is related to transmission parameters, right? This is related to transmission parameters, so that's why I'm taking T1 here. Okay, this is first two-port network, we can name it as a T1, and next two-port network, and this one is one dash terminal. Okay, and this one is two dash terminal, and these are the nodes. Okay, now you can take second one. Okay, second two-port network, which is also transmission parameters only, and so that I will take T2. Okay, the second two-port network name is what? T2. Okay, and here I will connect this port to one. So one of the output is connected to input to the second one, right? One of the output of two-port network is connected as a input to the second two-port network. Okay, second two-port network, and these terminals are 3 dash. So here these are the output of first two-port network, right? These 2 and 2 dash are outputs of first two-port network that is connected to uh, T2 as a input, right? So that I am taking like this. Okay, and these are the nodes from T1 to T2. Okay, so now you can give the variable names, which is very important. Okay, so if you carefully observe this, this one dash, generally this is first two-port network, so that I will take V1. Okay, but so this is first two-port network and first port, so that I will name it as V11. Okay, and current I11. Why I am taking I11? First two-port network, at the same time port 1. Okay, this is your port 1. Okay, because of port 1 I am taking V11 I1. Okay, when coming to this, so here the current direction is like this. Okay, so here we have I12. So this is first two-port network, so that I am taking I1, and this is port 2, so that I can use 2 here, I12. Okay, and here the voltage drop equals to V12. So V1 is related to port network 1, and 2 is related to port 2. So this is your port 2. Okay, and So same, so this port 2 is common for T1 as well as T2. For these two port networks, port 2 is common. So one of output is connected to another input as a input to the second one, right? So for here this one is I2. I2 is related to second two port network indication, and this one can be considered as port to one of this particular second two port network. Okay, and here the voltage drop equals to what? V21. I'm talking about this second two port network. I'm talking about this second two port network. So based on that, I will take the variables I21, V21. This I2 indicates second two port. This V2 indicates second two port network. But for this second two port network, this is the port 1 and this one is port 2. Okay. So now here we will consider V22 and this one is I22. Okay. So these are the variables. And now you can take for first two port network, for first one. Okay. So you can take V11 and I11. So for this, you can write the transmission matrix, that means transmission parameter, that is A1, B1, and C1, D1 into. Okay. So here the variables are what? I12 and V12, right? So now you can take V12 minus I12, right? This is your transmission parameter for this first two port network. In similar way, you can write for second two port network, for second two port network, and here we have these two variables, right? So V21 and I21, which is equals to, this is for second two port network, so that I am taking A2, B2, C2 and D2. Okay, and now the last two variables are what? V22 and minus I22. So these are the uh, transmission parameter for second two port network in an individual way, right? Not combined way. So we are taking individual transmission parameters for T1 as well as T2. Okay, this is for T1. Okay, and this is for T2. Clear? Now, but if you observe at this combination of port 2, okay, this is port 2 is common for T1 as well as T2. This is the common port. At this common point, you can take a observation. Okay, at this particular point, you can take a common point, that is V12 and I12. Okay, which are equal to, while taking I12. Okay, you can take directly I12, no problem. Okay, but if I am taking the direction of current in this way, okay, if I am taking the current direction in this way, so I will use the notation minus I12. Okay, I already told you transmission parameters is nothing but what? One port can be act as a source and another port can be act as a drive, so load. So always the energy transmission can be taken place from transmitter to, I mean, source to destination. So that's why we are considering one way of energy transmission. So but in our standard reference model we have opposite direction, so that's why I'm taking minus I12. Okay, these things already we covered in transmission parameters. So now I am taking V12 I12 here. Okay, so which is equals to V2. Here if you observe these two voltages, this V12 equals to what? V21 only, right? Across the parallel elements the voltage drop should be same, right? If you apply loop for these two things also, you are getting minus V12 plus V21 equals to 0, so that you are getting V12 equals to V21. When coming to this I12 I21, so both are in same direction only according to our transmission parameter assumption, so that's why I'm taking V21 and I21. Okay, so for example, if you are taking this is one point, so here the current direction is I12, and here the this is node, and here the current direction is I21. So that means I12 of amount of current entering into that point, that node, and the same amount of current can be leaving. Entering current is equals to leaving current according to KCL law, right? So that's why I'm taking I12 equals to I21, right? This is the matrix. Okay, now so in case of this opposite direction, okay, in our standard model that is I12, but in our assumption point of view, this is in this in this direction, right? So while taking this direction, you can use this particular minus I12 notation. So that here I am taking minus I12, right? So that V12 and minus I12 matrix can be replaced with V21 and I21, right? So now, so here, so this V1 V11 I11 matrix having V12 minus I12, which is multiplied with A1 B1 C1 D1, right? At this place, okay, you can replace with this particular thing, right? Now what you will get, just I am taking this particular thing. Okay, now you can substitute this value. Okay, so what you will get, V11 I11, which is equals to A1 B1 C1 D1. At this place of matrix, you can replace with this one. Okay, now what you will get, V21 I2, but already you know the V21 I21 value. So what is the V21 I21 value? So this is your V21 I21 value. Okay, this is your, this you can substitute at this place. Now what you will get, V11 I11, and which is equals to A1 B1 C1 D1, and at this place you can write this entire expression. So A2 B2 C2 D2 into V22 minus I2. Okay, so this is the expression. So from this is related to T1 two-port network, and this is related to T2 two-port network, right? So T overall equals to T overall equals to T1 into T2, right? That means what? So the ABCD matrix equals to A1 B1 C1 D1 and A2 B2 C2 D2. Okay, so T1 matrix multiplied with T2. Okay, this is the T overall. Okay, this is the conclusion, right? So here we have certain applications. Before going to, so that means first we will take conclusion for this. Transmission are ABCD parameters. ABCD parameters of overall two-port network. Overall two-port network is equal to the product of the matrices of ABCD parameters ABCD parameters of the individual network. And when coming to application part, applications, first one, we are using design of telephone system. This is one application, and we are using in microwave networks also. Microwave networks is nothing but high frequency circuits. Okay, high frequency. That means this method can be used in high frequency circuit design, and in radar applications also we are using this type of method. And this is about transmission parameters, otherwise ABCD parameters. Okay. So in our next session, we will discuss about inverse transmission parameters. Otherwise, we can call it as A dash, B dash, C dash, D dash parameter. Okay. Thank you.